Welcome back to theCUBE here in Palo Alto for a special presentation, Scaling the Agentic Era with CoreWeave Cloud. I'm John Furrier, host. We got two guests and a special appearance. We got Dion Harris, Senior Director, Accelerated Computing, Product Marketing at NVIDIA. Dion, great to see you.
Thanks for having me again,
Thanks
John.
for coming on. And
Absolutely.
Harsh Banwait, Director of Product Management at CoreWeave. This is the big day, the big news is out, and you're showing workloads. We have a special guest, the Superchip, the Vera Rubin Superchip. So technically, Vera Rubin Superchip is here on the interview. It won't say much, but you guys will chime in for it. Thanks for coming in.
Absolutely.
Dion, first question to you on the NVIDIA side. This is a huge accomplishment. Last year at GTC, we saw the Pareto curves.
Yeah.
Jensen laid that out in Taipei, talked about the era of useful AI. What's the architectural and the key innovations of Vera Rubin? Why is it important? What's that do to the AI economy?
Yeah, so first let me just sort of unpack that statement about what useful AI means. Essentially, if you look back on the trajectory of AI, Hopper was really about training capable foundational models. And so that enabled the ChatGPT moment. That showed us what was possible in terms of harnessing the power of AI. Blackwell was about introducing new inference at scale. In fact, we talked about it as the era of AI reasoning, right? Reasoning models, DeepSeek, O1, they introduced new capabilities that allows you to deliver better intelligence, within the same sort of power envelope. And so that's why Blackwell had incredible leaps in terms of performance per watt and overall intelligence. In fact, we showed that it could deliver 50x more performance versus Hopper for inference. For Agentic, this is sort of where we're actually getting real work done. So we're taking those foundational models that were trained on Hopper, we're taking the new AI reasoning capabilities that were delivered through inferencing on Blackwell, and now Rubin's going to unlock the Agentic era. And so Agentic is basically where you're taking not just a model and doing single shot inference, but the model itself does planning, it has skills, it has subagents that then go and break down a problem and solve it to do real work. In order to do that, you need a different type of infrastructure, you need different type of operations in order to facilitate that. So that's why when we say Vera Rubin was built for agents, it was built to enable that new workflow, the CPUs, the GPUs, the storage, all of that coming together to unlock these agentic workflows.
It's a new characteristics of the scaling up of the evolution, which is an always on. And Goldberg said on my fireside chat with her, it's a living thing. It's always on, it's training, it's inferring.
That's right.
Harsh, how do you take this and you platformize it and operationalize it? Because what you guys are doing with the CoreWeave Cloud is taking advantage of all these innovations from NVIDIA and productizing it. Correct. What does it mean for the customers? What does it render into? How do you operationalize it? What does it mean?
Yeah, again, I think like when we first saw a view of Grace Blackwell a few years ago, we saw that rack scale was the future. And when I started thinking of what does our product portfolio need to look like, not just at a surface level, but also from the ground up, how do we build our data centers? How do we build our Kubernetes service? How do we provide telemetry on these products? All of that had to be focused on how does that happen on a rack scale product? Because in a rack scale product, it's not just a bunch of compute nodes that are sitting isolated from each other. They're shared infrastructure, all of them need to interact with each other. So for us, it started from the ground layer up. It's how do we design our data centers to be able to deliver the power and the cooling that's needed for these racks. And from a product level, we started looking at things like our CoreWeave Kubernetes service, where we said, okay, if a customer needs to place their workloads within a single rack, because if you take the workload outside the rack, the performance that you're going to get from node to node, it's not going to be the same. So how do we expose things like NVLink labels? How do we expose fabric labels to a customer? And how do we make it easy for them to essentially, when they're scheduling a workload or for an agent to identify where does this next workload need to be so that when two nodes are talking to each other, they're doing it as fastest means possible. We took that to Sunk, where we supported the topology block plugin so that you can look at a block of 18 nodes and see, okay, if I need to run my workload across 18 nodes, these are the available racks for my customers. And then the last thing is from a telemetry standpoint, we looked at mission control. And we looked at mission control from a few different angles. First was bring up. Throughout the vast majority of time, we would bring up nodes independent from things like PowerShells and other objects, but now we need to be intelligent about okay, the PowerShells and the NVLink switches and the CDUs need to work with the compute nodes. So how do we serialize as much as possible? Yeah. That's where we invested in our rack lifecycle controller, and then try to surface all of that information through our cabinet wrangler, cabinet visualizer dashboards to customers to get a complete view of rack level products and not just like a compute level product.
Yeah, I remember talking to Dion. We were talking a few years ago when we first met about large scale systems, and Jensen calls it the AI factory. And then at that time, we were riffing on this idea of an operating system. Yeah. You gotta, it's not just a server. It's like a collection, it's a system. And now you hear that all the time. I mean, Jensen said it on stage a lot, operating system, but now in the industry, the operating model has become the language. Our operating model, this speaks to the AI economy. So, you know, Harsh, this is not easy to do. It's an operating system. What you just talked about was scheduler, you know, runtime, Kubernetes with the Superchip. It's a whole nother, I mean, it's a supercomputer, we don't know that, but it's not easy. What was the hardest thing to do here? Because you got the new, I would call it hardware, it's a system. I mean, look how small that is. I mean, that is like incredible.
Yeah, so I think like from our standpoint, the hardest thing to do was just like when all of it comes together, how does it look and feel in practice? We've read the specs, everybody's seen what it might look like, and this is where the reason why we're so proud of our bring up is we brought it all together, kind of went through the validation flow to make sure that the Vera CPUs work with the Rubin chips, to work with CX9 NICs, to work with the BlueField 4 DPUs. So for us, it was like just making it sure that all of these components talk to each other and act as a system to essentially unlock that level of performance.
It's nice to see the collaboration between NVIDIA and CoreWeave. And Dion, I want to ask you to talk about the differences, but first I'll just say after Taipei, obviously the economy piece is there because the inference with training and agents is really driving revenue and business model transformation, a whole nother discussion. But at GTC, when Vera Rubin was laid out, the slide with the Pareto curves, looks as a maturing product portfolio. You got an entry level, you got a mid-range, and now you have a high-end flagship product. What does that mean for you guys? And explain the differences between Vera Rubin and Blackwell, because you mentioned agents. What specifically is different? I get it, people see the difference, but when should they be thinking Vera Rubin, Blackwell? What's the difference between the two?
That's right. Okay, well, we'll just, like I said, just go back in history a little bit. When we went from Hopper to Blackwell, reinvented the data center. Now introduced, as Harsh said, the rack scale architecture. Systems were going to behave as a single rack scale unit. It forced operators to think differently about how they operated the system, built the system, implemented it. So as we go from Blackwell to Rubin, we're actually thinking about it at a pod level now. Like in other words, of course, we have the NVL72, which is a CPU GPU, again, you know, comprised of these Vera Rubin Superchips, the NVLink switch trays, but then we're also introducing standalone Vera CPU racks to do a lot of the orchestration that's involved in the agentic workflows. We're also introducing BlueField STX racks, which help manage all the storage because you have to move lots of data around that workflow in order to enable those agentic systems. And then of course, when we talk about scaling across the data center, we have our BlueField racks, which is basically enable you to not just run across a single rack, but run workloads across the entire data center because agentic workflows will require that. And so understanding that as AI has moved, like we said, from generative to reasoning and now to agentic, it now forces us to rethink how we lay out the data center and how we operate, not just on the system level, but on an AI factory level.
Talk about the performance numbers, just kind of high level on tokens, transfers, inference. Highlight some of the key points on where the performance kicks in.
Yeah, so what's interesting, if you look at this super chip, Rubin itself, the two chips deliver about 100 petaflops of AI performance in just this super chip. When you look at actual delivered application performance, it's about 10x. And so this is one of those examples of extreme co-design. In other words, if we were just relying solely on transistor counts and flops, we would be sort of in that 1 to 2x performance factor range. But by leveraging the full NVL72 rack, we've improved the overall NVLink speeds. We've improved the speeds at which the NVLink C2C talks to each other. Now CPUs, GPUs can talk at 1.8 terabits per second. We've also improved the overall efficiency in how it's delivered in terms of having it 100% liquid cooled. So again, all these innovations are several different layers of improvement, but they all translate into that 10x improvement of overall inference performance. And then when you look at sort of inference for agentic, it has a different sort of requirement in terms of the interactivity that's required. So it's not just about throughput, but also opening up new regimes of interactivity so that agents can talk to agents extremely fast. So we're not only able to deliver more performance, but also unlock new areas of service levels and interactivity for agentic workloads as well.
Yeah, thanks for sharing that. This is why I love the computer industry. Things just get faster, smaller, less expensive. Let's take a moment to do a walk around the Superchip here and point out what's what. I mean, obviously I can see them. Where's the Rubin? Where's the Vera? Where's the networking? Just do a little walk around. Show us where's what on the Superchip.
Sure, yeah. So this is the Vera Rubin Superchip, like we talked about. And essentially you have the cold plates over the chips themselves, so you can't see them, but essentially you have two Rubin GPUs that sit here. They connect via NVLink, and they connect into that NVLink spine that you've seen Jensen hold up on stage from time to time. And this allows them to talk to each other. Every GPU can talk to each other at 3.6 terabytes per second, full line rate. So that's what gives you that incredible sort of coherency of all that memory, all the compute. And they also have a Vera CPU, which also sits on the Superchip. This Vera CPU has 88 custom Olympus cores. We redesigned the cores. They're ARM compatible, but it's a total custom NVIDIA design core. And you can't see it in this particular Superchip, but connecting these systems, we also have the BlueField 4 DPU for the north and south traffic. And we also have CX9 cards, which connect to the scale-out fabric. So if you're looking at a compute tray, you would see two of these Superchips that sit there, connect via the CX9 NICs, and then you would also have the BlueField that also allows you to enable cross storage and the data plane as well. So all of this within the compute tray delivers incredible performance and again, efficiency in terms of how they communicate with each other and across the AI factory.
You know, it's really incredible to look back at some of the rack standards, go to OCP, Open Compute Project, and what's gone on in the open source community has been phenomenal. Harsh, based on what Dion had said, this is a huge opportunity to, you mentioned rack scale.
Correct.
There are a lot of efficiencies in rack scale systems that people might not notice, like leveraging the GPUs, make sure they're always utilized, engineering some of the systems so that it's cohesive, but yet highly functional. What's this look like from a CoreWeave standpoint? How do you translate this for the AI builders, the AI labs? You have a lot of the labs as customers. Hen said, you know, the top producers are using you.
Yeah, I think like, again, it starts from looking at the reference architecture for some of these systems to see how do we unlock the maximum amount of performance and at scale. Dion talked about like pod level architecture. When we talk to customers now, they're not just buying single or two racks. They're buying tens of thousands, hundreds of thousands of GPUs at a single time. So for them, it's important that we scale in a uniform manner. And I'll use an analogy to what Dion said that I use with my internal teams. When we talk about a new GPU, like I want my teams to think about a new GPU in the context of a car. GPU is just a car, but what we have built here is not just another car, we've built like another city. So when we talk about a rack scale system, it's not just that we have a new car, we have new networking, which is new streets, we've unlocked what were the hotspots. So we've tried to make a system level efficiency happen for our customers. And from our standpoint, the way we do that, starting with reference architecture, but then talking to our AI labs and trying to see what is it that they're looking for. Is it that they're looking to train their next generation model in a faster period of time? They're trying to train like a larger model. We've looked at some of the numbers. So like if it takes like a fourth of the GPUs to train a similar sized model, then it's a cost saving. But I'll tell you, like a lot of the conversation I have with customers now is like, how do I train a larger model? Or how do my teams actually iterate on the models that they were training so that we can either put out a wide variety of models, or we can put out like better models at a faster speed of time. And when it comes to like inference as well, I think economics on inference is something that a lot of customers are thinking about. So for them, if they can look at their token costs and they can see that they can generate 10 times the number of tokens for the same cost, their employees can do a lot more with the same budget. Last year we saw Mistral was one of our first customers that adopted Grace Blackwells, and they saw about 2.5 times improvement, like right off the gate with Grace Blackwell, and that was just when we first launched Grace Blackwell. So I'm very excited what Vera Rubin is going to enable for our customers too.
Dion, I get a question a lot from folks. It's like, okay, Vera Rubin's the hot super chip. NVL72 is in the naming. That might not be well understood from an architectural, and then how that translate as an architecture. Talk about the key things around Vera Rubin NVL72. What is the key? Is it performance? Is it everything? What does it mean?
No, that's a great question. So Vera Rubin NVL72 stands for Vera Rubin NVLink 72 GPUs, essentially. I'm just trying to decouple the naming there, right? And essentially what that means is you have 4 GPUs per compute tray, right? And so that allows you to have all of these systems talking to each other. They're connected via NVLink, that like we talked about before. You have 18 trays, so all the 18 times 4 gives you 72 GPUs. Now what makes that incredibly important is that compute density allows you to stay on copper longer. Like we were talking about this earlier, having these NVLink backplanes where you're basically blind mating them into that NVLink spine, that gives you full line rate communication from every GPU to every other GPU. So that's what really gives you the performance efficiency, that extreme co-design that we talked about. But it's not just about the actual performance, it's also about the reliability. I think as Harsh said, when you're deploying AI factories at hundreds of thousands of endpoint scale, you need to make sure that it's going to be not just performant, but extremely reliable. So in our NVL72 Vera Rubin rack, we actually redesigned the entire engineering and mechanicals of the rack itself. So for example, within the compute trays, they are 100% liquid cooling now. So you don't have any wires or any cables, so that you can literally assemble and disassemble it within 5 minutes, right? And so that gives you incredible efficiency, not just from a manufacturing standpoint, but from the operational implementation standpoint. It also has hot swappable components. Like you see these inlets here for the liquid cooling, they have detectors like within milliseconds. If it detects a decoupling, it'll automatically shut off the valve to ensure that there's no spillage. So having those different implementations of operational efficiencies and reliability efficiencies was really how we thought about redesigning the rack. We wanted to maintain the same form factor because, like I said, when we went from Hopper to Blackwell, it was a huge shift.
So NVL72 is the rack scale.
It is the rack itself.
If it was a SKU, it'd be a SKU, but it's all the super chips are all in there, engineered the way you talked about it.
Yes.
Harsh, talk about this impact for you. How do you integrate this into CoreWeave? Because he mentioned, Bluefield, all this other, you got HBM, you got storage, everything's going on around the super chip.
Correct. Yeah, so from our standpoint, I think the way we take that technology and translate to our customers is through Vera Rubin-based cloud instances, and each instance on CoreWeave essentially comes in with its own set of CX9 NICs, with its own Bluefield 4 DPU, and our systems essentially are also responsible for cooling it, monitoring it, and serving it to our customers. I mentioned a little bit earlier of how do we expose like those NVLink labels, those fabric labels at both like a pod level so that customers can see where exactly is my workload sitting. If I want the maximum amount of performance that I need from a training job or an inference job, like where should I be actually serving it? My job is to make it easier for the customer to consume it, no matter what level they're
So I have to ask on the agentic piece, because Dion brought this up, this is the key positioning of this offering. It's going to hit this always on, smart enterprise, whatever word, intelligence and business, whole nother level. How do you configure this to take advantage of that agentic? What's different about, how do you stand it up? You guys validated the first workload on Vera Rubin, which is a huge accomplishment. What did you learn, and how should people think about configuring, managing for agentic so they get it right out of the gate?
Yeah, I think like I would actually go ahead and say I don't want my customers to think about configuring and managing it. I want to do it for them.
Call CoreWeave, we'll manage it for
correct. you. I think like some of the improvements that Dion talked about from a mechanical standpoint are going to be minimal when somebody else looks at it, but as an operator, they're immense. For me to be able to have 100,000 of these in a data center, my job is to make sure that they're as efficient and performing at their theoretical peak level, right? So,
and what are you optimizing for? And that, because you're the operator, you're running the customers. I get that. So you have to think about making this always on. What are the key things you optimize for?
Yeah, so from our standpoint, one of the key things we look at is like model flops utilization. So if a customer's got a set of GPUs, they have a theoretical amount of T flops, B flops, E flops. How do I essentially ensure that they're able to make good use of all of them, whether it is for a reason that like a data center is down or something else is going on? My job is to make sure that the system's been validated, that I can detect that something is about to go wrong, and I can replace that, hot swap it by taking it out gracefully out of the customer's cluster. And from our product stack, like this is exactly what Mission Control does. Is it can recognize when a customer's rack has redetected something. It can tell the customer, you can essentially gracefully shut down this system. We will replace it with another rack, and the customer can be whole again.
I mean, Michael Dell couldn't hold back. He posted on X a picture of the rack scale. He was so proud. Take us through what you guys did. We're going to see a video, so give us a teaser of the workload that you guys validated. Take us through how that went. What was the key learnings? What was the takeaway?
Yeah, I think I'll just say, like, I think all of us are hardware nerds, so whenever we see any new generation of hardware, we can't wait to take pictures. We can't wait to like share all about it. So what we did was, you know, like I mentioned, there's so many new innovations with this. There's CoreWeave is validating with like all the 6 different chips that are coming out.
Dion, take us through the cooling. This is one of the key innovations on the Superchip. I've never seen it this tight and compact. You mentioned the board and the Rubin and Vera and all the connections, but what I'm looking at there is a cooling piece. Take us through the value and what's differentiated.
So all the mechanicals and thermals on the Vera Rubin compute tray have been completely redesigned. One of the key innovations is, in addition to being 100% liquid cooled, it actually can operate at 45 degrees Celsius. And the reason why that's important is operating at a higher temperature allows you to use more power for compute and less power for chillers that are basically cooling the liquid as it goes back through the closed loop system. And that's really important because it's another example of where the system design impacts not just how you operate it, but actually how you build and design your actual infrastructure around it. So making sure that you have, you know, the closed loop liquid cooling system, making sure that you've optimized and built for a fully liquid cooled environment is really a huge opportunity to deliver savings and performance efficiency. Again, more performance per watt is going to drive more revenue.
Harsh, talk about the components to manage it, because I think cooling them, whoa, that's more complexity. What's, you know, we heard from Hen, there's a lot of software involved in the CoreWeave system. How do you manage this? Is it a single plane of glass? How do I have AI working it? Take us through how you manage that.
Yeah, absolutely. So for us, what we do is we essentially serve it as a part of like CoreWeave's Kubernetes service or our bare metal as a service, where customer can get each of these as a bare metal instance or a Kubernetes instance on CoreWeave. And as a part of each instance, customer gets 2 of these Superchips. So like each compute tray is its own instance. Each of them has its own Bluefield DPU. Every CoreWeave Kubernetes instance has a Bluefield DPU, and customers provision it through our Kubernetes stack. Then once they've got these systems, it goes through our validation process at a bring up level, but also passive tests once the customer has these systems. And then the customer can choose like what, where and how to schedule their workloads on CoreWeave. So there's a couple of different ways for them. Either they can go through CKS and pick, okay, I want it in this NVLink fabric or this rack. They can choose through Sunk to decide if you are an avid user of Slurm, that this is what I want to use. Or you can also go through our dedicated inference stack and choose a particular hardware if you're serving inference on these systems.
Dion, explain how the Superchip scales in the NVL72, because this is an innovation opportunity for your partners in the ecosystem.
Absolutely. So when you look at the Vera Rubin compute tray, it's comprised of 2 of these Superchips. And so that means you have 4 Rubin GPUs that are in each compute tray. You have 18 compute trays. Now the way they connect to each other, we have these NVLink ports on the back. They blind mate into that NVLink spine. Each of those connect into 9 NVLink switch trays. All of those switch trays allow all of the GPUs to talk to each other at full line rate at 3.6 terabits per second. Now the reason why that's incredible is it allows it to behave as a single GPU. And that's really the genius of this rack scale system, is that it allows you to scale memory, scale compute, scale all the fabrics. so that it can talk to each other at full line rate, so that GPU number 1 can talk to GPU number 72 at the exact same speed. And so this is what gives you a very consistent, reliable way to scale your workload across the entire rack. Now, when you scale out, that's when you're leveraging the CX9s, and that's where you start to leverage our Spectrum-X co-packaged optics network. And so that allows you to scale out efficiently across the racks, so that as workloads scale across NVL72s, you can run those efficiently as well. And so all these elements need to fit together extremely well. That goes back to the idea of extreme co-design, and it also needs to integrate tightly with CoreWeave's operational metrics to make sure that they can deploy these systems efficiently as well.
So as one large rack scale gets as one system, they all works together very cohesively, but then expands into one bigger system with scale across. Is that right?
Absolutely. So that's where the Spectrum-X co-packaged optics network comes in. And then, of course, it also needs to talk to storage and get data in and out of the rack systems as well. That's where the DPUs come in. And so having these various processors, we talked about the 6 chips, that's really why we have them, so that they can work in concert to deliver performance to scale up, to scale out, and to access those data and control planes. And then, of course, we have the standalone Vera CPU, which is, again, a revolutionary ARM-based CPU, which delivers incredible performance. In fact, it's about 1.8x more performance per core, which is an important metric when you're talking about agentic workloads. So that performance per core is incredible for all the tool calling, all the orchestration that happens in agentic workflows as well.
Harsh, you're a product person. What he just said is a dream scenario. Take us through how CoreWeave, how you guys look at that from a product standpoint, because I mean, he just laid out a series of technologies, both scaling up and across as one system. That's a lot of software, that's a lot of hardware working together. How do you make it all work?
Yeah, I think like from our standpoint, we have to look at it from our customer's lens. As they're building and serving these agents, it's very important that the system performs as like one big GPU when we're looking at NVL72, because when you look at agents, there's so much context that builds up over time that the agents need to store. And from our customer standpoint, this is where they expect us to ensure that like the systems are up and running at the performance that the customers expect. And this is where we also lean on NVIDIA's reference architecture for these systems, where each compute tray comes with CX9 NICs, comes with BlueField-4 DPUs, as well as from when we're looking at scale-out fabrics, we're leaning on Spectrum-X as well as InfiniBand. So from our standpoint, we offer flexibility for our customers depending on whatever it is that they are looking for. From a workload standpoint, from a use case standpoint, we offer both, and our fabric can then scale up to over 120,000 GPUs. So no matter what the workload is, we're ready for it.
Yeah, you got the capabilities, and what's beautiful about the headroom there is you can start tiering performance. Certain agents get tier 1, tier 2, so you can look at policy and scheduling, all that kicks in together.
Correct, and including like sandboxes too. So recently we've introduced a sandbox product. So a lot of these agents, sometimes you're running experiments in them, sometimes they're running some code. You want to give them a safe environment where they're not essentially going out and ruining something else. So we introduced CoreWeave sandboxes recently to essentially also make it easier for our customers to run their agents.
And that performance isolation is why I mentioned the per core performance is so important for the Vera CPU, and why we optimized the design of the Vera CPU to enable that. And so that's an example of how we were purposely building a CPU that was for the agentic era, not for the cloud core computing era.
What's the availability of the system?
Yeah, our team's hard at work on bringing a bunch of these up, and we're looking at later this year to get this in the hands of our customers.
What's your outlook for this AI economy? Just general thoughts, because you know, NVIDIA, you're leading the way, starting to say, hey, the AI economy, you're building it at CoreWeave, you're supplying it, Dell's making the racks. It's a huge, whole nother change in the computer industry.
That's right.
And looking back, it's like, okay, servers, great. Now we're talking about large scale systems and racks operating soon in concert.
Well, I would even think beyond that. I think it's not just systems and racks, it's truly the end-to-end AI factory, like where you're looking at the construction, the design, you know, the engineering that goes into the building itself, the land, power, and shell. All those elements now need to be thought about sort of in concert to make sure that you're going to deliver the best performance per watt, so that you're maximizing the flops that are coming out of the systems, but you're also making the best use out of the energy that's going into them. So our view of the world in terms of where AI factories are going it's going to require that industry-wide, ecosystem-wide collaboration. And so I think, this is an example of it, and the fact that we're collaborating and co-engineering, not just at the system level, but literally at the AI factory operation level. But that also extends to the grid and how we're interfacing with power generation sources and making sure that we can make good use of those resources. So I think the outlook is very strong, and the fact that we're taking such a collaborative approach from an ecosystem standpoint, I think will bode well for the entire industry.
Yeah, 5-layer cake of computing. Harsh, this is a great opportunity. I mean, it's not moving up the stack. The demand at all levels of performance in the stack has changed. You guys are building out the infrastructure. What's your view?
I think Dion mentioned a good point about like co-innovation. A lot of people bring up and say, okay, this is great, but like, what's so special about it? The engineering behind the scenes between NVIDIA, Dell, CoreWeave starts quarters, if not years in advance. You cannot build a data center like within 60 days if you're just looking at a hardware for the first time. So you need to be able to understand what is it that the infrastructure is bringing, what is it that it's going to need from a power, cooling, engineering standpoint, so that when the hardware actually lands, when the firmware actually lands in front of you, how do you essentially get it going and make it useful for your customers as soon as possible? And yeah, again, from a demand standpoint, I'll use the same words like my founders use, demand's insatiable. Our customers can't get enough. You
got a Superchip, and it's got extreme co-design. Dave, a lot of time we're joking, extreme AI could be the next kind of buzzword.
That's right.
Pushing the envelope as you guys push the frontier. Thank you for spending the time unpacking that. It's a lot of great stuff. Love the Superchip here, and it looks awesome. Thanks.
Yeah, awesome. Great.
All right, I'm John Furrier here, theCUBE in Palo Alto, scaling the agentic era with the CoreWeave Cloud special presentation. Thanks for watching.